Thanks for the introduction. So first, I'd like to thank the organizers for organizing such a great conference and for inviting me here. It has really been a great time. So I'm going to talk about stable homotopy groups of spheres. So this is joined with Bogdan Gregory, Dan Isaacson, and Guozhen Wang. So let's start with the definition. So the stable homotopy groups of spheres are defined by based homotopy maps from the n plus k sphere to the n sphere, and when n is big enough, it has nothing to do with n, so we call this the k stem. So what do we know about those groups? So Sarah told us those are all finite abelian groups at positive stems, so that means we can compute one prime at a time. We also have the composition to form a graded ring, like it's commutative in the graded sense. So we also have some higher products, like some matrix total brackets, as you heard in Tyler's talk. So we'd like to understand as much as possible for those structures. So before we compute anything, there's a warning, which is called the Mahoward uncertainty principle. So this is named by Doug Ravenel, and it also appeared in Pogger's note. So what this says is, I'm going to call this the first Mahoward uncertainty principle. So any spiral sequence converging to the homotopy groups of spheres with an E2 term that can be named using homological algebra will be infinitely far away from the actual answer. So what this means is like having any Adams kind of spiral sequence whose E2 term is can be computed by homological algebra, but there's still infinitely many of differentials that needs to be solved. That does not come from the algebra. So in the spirit of this first principle, and also like from my precious conversations and interactions with Mark Mahoward, I'm going to propose the second Mahoward uncertainty principle, which says that any method that computes non-trivial differentials in such a spiral sequence will also leave infinitely many differentials undecided. So what this means is that we should really combine all the methods we have to do more computations. So each method alone will hit the wall at some point. All right, so now also I'd like to quote the phrase in Paul's note, which says that nonetheless we soldier on. So I'd like to first review some history, like how we computed. So the first breakthrough is by Sarah using the Sarah spiral sequence up to the 8th stem, and now later by Tilda using the EHP spiral sequence up to the 19th stem. So both methods are the unstable methods. They're both inductive. And in particular, the stable range is part of the unstable range. And those computations are over Z. So after that, we have the Adams introduce the Adams spiral sequence, which exists at every prime P. So the E2 term is X over the string algebra, and it converts to the P part of the stable homotopy groups of spheres. So we also have the Adams-Novikov spiral sequence, so based on the Brown-Peterson spectrum, whose E2 term is also an X group, and is X over BP star BP. So now we have a question. So we have two spiral sequences. So which one is better? I guess that's not a very good, question. Somehow I can't see the screen on the computer, so I'm just going to do this. So, all right. So, well, the answer kind of depends on which prime you're working on. So we have two spiral sequences. So what are all the connections we can have? It's good to use both methods, of course. So there's a map, which is the time reduction theorem. Oh, it worked again. So there's a map from BP to HFP. So that induces a map on the E2 page. So that will preserve the filtration on the E2 page. So however, whenever we have a map of spiral sequences, there's a very usual phenomenon happens, which is called the jump of filtrations. So what that means is that taking any homotopy class, so that should survive in both spiral sequences, but the detecting element on the E2 page may have different filtrations. So that means on the E2 page, this map actually doesn't tell you those two elements are connected. So for example, if you take the image of J elements in the stable homotopy group spheres, so the Adams-Novikov filtration are usually on filtration 1. But the Adams filtration could be as high as you want. So you don't see this kind of connection on the E2 page. So that's another good news. So, but there's a better connection. So I like to call this connection the Miller square. So what happens is that there's another X group, So I don't want to go into details here. The point is that this X group is the E1 or E2 page of two other spiral sequences, and one converting to the Adams E2 page, the other one converting to the Novikov E2 page. So the Cartan-Eilenberg spiral sequence comes from some extension of Hopf algebras, and the algebraic Novikov spiral sequence comes from this graded thing for BP star. And there is a change of ring isomorphism that you can identify the starting point at the same X group. So this gives another way of comparing the two spiral sequences. If you want to do something, we can just go back from the origin, like in here, and do things. So this is like a map. There are two ways to go to the answer we want. What's more interesting is that at R primes, the Cartan-Eilenberg spiral sequences actually collapses. So what this means is that there are two ways to go, but this way there's nothing happens here. Well, there might be extensions, I don't know, but if we can choose at R primes, if we can choose between the Adams E2 page or the Novikov E2 page, one should probably go from here. Well, provided if we know how to compute the E2 page. Because if you go from here, it's like those two parts together is this one part. So it's like half the job is already done. So also there's a theorem by Hinz-Miller which says that the Adams D2 differentials, like differentials in here, correspond to the algebraic Novikov D2 differentials. So I'd like to emphasize how powerful this theorem is. So all the differentials in the algebraic Novikov spiral sequence can be essentially computed by, say, embedding into the Kobar complex. Because the whole spiral sequence is algebraic, we can compute as much as we want. However, on the other hand, the Adams D2 differentials, because it actually converts the homotopy spheres, so by the spirit of the second Mahower's uncertainty principle, there's no universal way of producing differentials like in here. But this gives the connection of producing at least the D2 differentials. I also want to mention that based on this technique, so Hinz-Miller proved what is now called the telescope conjecture at Carmack level 1 at all primes. And of course, at prime 2, that's proved by Mark Mahower because that's his prime. So, all right, so for different primes, you probably want to choose different spiral sequences. The bigger the prime is, you should really want to do Novikov. The smaller the prime is, you want to do Adams. So my talk will focus on prime 2 computation. So before I do that, I want to give you some update on what's going on at other primes, just a little bit, what the record is. So at prime 3, Nakamura and Tangara, they're using the Adams spiral sequence, and Doug Ramnall is using the Adams-Novikov spiral sequence. It's computed around the 108 stem. And P equals 5 in Doug Ramnall's green book is computed around 1,000 stem. It looks like a much bigger number than it is, but according to Doug, they're both about the dimension P cubed times V1. So you should just plug in P equals 3 and P equals 5, so you see those two range are about the same in this sense. And if you plug in P equals 2, you find the number 16. That's a rounded range that Toda has. So, all right. So at prime 2, we should really use Adams spiral sequence. That's still the most effective way to compute things. All right. So now, for any spiral sequence, there are 3 questions. So the first one is how do we compute the E2 page? The second one is how do we compute all the differentials? And the third question is how do we solve all the extension problems? So for the E2 page, this is actually known a long time ago in Peter May's thesis. So Peter May construct the May spiral sequence giving a filtration on the Steven algebra. So there's a trigraded spiral sequence converting to the Adams E2 page. And this is very computable. So what happened is Peter May computed his spiral sequence in a much bigger range. So we have the Adams E2 page in a much bigger range. Then he compared with Toda's computation, because we already know the homotopy groups, to deduce backwards what are all the Adams differentials, then using the product structure in the Adams spiral sequence to push more stems. And he stopped at 28 stem. So what happened is there's an element in pi 30, which is the covariant element theta 4. So at that time, he couldn't decide whether the element survives or not. That's why he stopped at 28. So now we have a bigger range. We know the E2 page as much as possible by the May spiral sequence. I'd also like to mention that now we have different programs that also does this job. So for example, we have Bob Bruner's program or Christian Nasser's program. And I'm sure there are other programs. So the E2 page is not really a problem. The problem is the differentials. It's also the spirit of the second Mahover's uncertainty principle. So Barrett, Mahover, Tangara, they are computing the atoms differentials up to the 45 stem. So there are two major techniques they are using. So the first one is to play the interaction between the Massey products and total brackets. So Massey products are defined on any atoms ERN page, and total brackets are defined in homotopy. So there's a theorem by Moss saying that if we have a Massey products where each input is a permanent cycle, and the corresponding total brackets also is well defined, and under a certain technical condition called node crossing differentials, then the Massey product will converge to the total brackets. So this is very useful because this produces ways to show that some low filtering elements are actually permanent cycles to rule out a lot of possibilities. So another very useful method is through some finite CW complexes, because it can translate problems of differentials to extension problems and the other way around. So I'd like to say something about this method. So I also want to call this the Mahover's trick. So for example, let's take the two-cell complex, the covariable eta. So we have a covariable sequence that gives us a short exact sequence on homology, which gives us a long exact sequence on X groups. But each X group is the E2 page of its own atom spiral sequence, which converges to the long exact sequence of the homotopy groups. So the idea here is non-trivial eta extensions in the atom spiral sequence in sphere will correspond to differentials in covariable eta. So what I mean by this is that, so suppose we have, like, the boundary homomorphism in homotopy is just by multiplication by eta, and the boundary homomorphism in X group is just by multiplication by the element detects eta in the E2 page. So if I have a non-trivial eta extension, that means there are elements in here, they're connected by this boundary homomorphism by times eta. They both are homotopy class, that means they're both a permanent cycle lives in here that survives in the spiral sequence. However, the non-trivial extension means that they're not connected by the algebraic eta. So therefore, there will be two dots living in the X group of curve eta, but there are no homotopy class living in here. So what happens naturally is there's a differential connecting them. So that's the differential in curve eta. So of course, so like what happens in practice is much more complicated than this, because those two elements are not connected by the algebraic eta. There might be some other elements connected to this, and the other element may support differential and so forth. So we may have to do a zigzag, and to be careful using naturality to deduce things using the jump-off filtration, that kind of argument. But this trick is very, they use this trick extensively in their computation up to the 45 step. All right, so that's the story in the 70s. So later on, there's Kochman introduced another method in the 90s, which is really smart. So that's the Atiyah-Herzberg spiral sequence for BP. So he computed around the 60 stem. So the idea is that we know the homology of BP. We also know the homotopy of BP. So we can deduce reversely what are the homotopy of spheres. So, but however, after a few years, I don't really know this part of history. I guess it's like Mahover noticed something doesn't look right to him, and then they find a few errors. So based on the same method, they corrected a few errors. And later on, very recently, Dan Isaacson discovered more errors in that range. So I don't really understand how this method works. It's also heavily computer-based. I can follow the first few steps, not the whole thing. So I don't really know what happened. But Dan Isaacson's method is very compatible with the classical atoms computations. So I can follow that. So all right. So now I'm gonna talk about the new methods. So in 2014, Isaacson using the motivic atom spiral sequence over spec C and computed up to the 59 step. So there are some motivic background, but I'm not going to mention them. So the upshot is in the motivic category, as you heard in Doug Ramner's talk yesterday, there exists motivic Stingray algebra. So we have motivic atom spiral sequence, motivic atom-Novikov spiral sequence, motivic May spiral sequence, and everything. So the whole computational tools exist in the motivic category, at least over C. And the work are due to, I think, well, of course, there are Wolski, Morel, Hukrich, Ormsby, and Duggar Isaacson. But Isaacson himself is really the one who pushed the computations and start to have results back to the classical homotopy category. So here's the idea. So we have a map from the motivic category to the classical category. That's the Batty realization. So this functor gives us a map of spiral sequences. So this is just the motivic atom spiral sequence converting to the motivic like p-completed sphere. And here fp tau like is a one generator polynomial ring. That's the motivic homology of a point. And so the motivic thing, everything here is bigraded, so the spiral sequence is actually trigraded. So this tau element is really something unique in the motivic category over spec C. So it actually survives in homotopy. You can realize as a map between p-completed spheres. So a natural thing to consider is to form this two-cell complex, covariant tau. So Dan Isaacson also used this Mahavir's trick for covariant tau to deduce more things. So what he did is that he used the computation up to 45 in the classical case, and then deduced the motivic computation up to 45 stem. Then use this actual grading and the product structure and this Mahavir's trick to deduce more stems in here, then use the Batty realization to push down to get more classical results. So the actual grading is really what's helpful in here. In 2015, Gordon Wang and myself, we developed another method. We call this the RP infinity method. So what happened is Dan Isaacson got stuck at 59. So there are certain differentials he couldn't prove in 60 and 61. So that's why he stopped. So using the new method, we were able to push 2 more stems. And before we used the RP infinity method to prove more stems, the 3 of us discovered another method. We like to call this the motivic covariant tau method. And we compute up to 90 stems and it's still ongoing. So the motivic covariant tau method is really not really the same as Isaacson's method over here. There's something else. And it's, as you can see, it's like much more powerful. So I like to spend most of the time on the covariant tau method. But before that, I will spend a few minutes on the RP infinity method. Any questions so far? All right. Oh, here's the chart of the atoms spiral sequence. Maybe I can like zoom in a little bit. Like so all the stems are like vertical like columns. All the segments in like negative slope are differentials. So those are the range of the differentials computed, and this is the chart only up to 80. So we haven't made the classical chart up to 90. We only have the motivic ones. So this is the classical chart. So of course, when I say we compute up to 90, there's still a few differentials left by this method due to the spirit of the second Mahavir's principle. Yeah. Color code, it's just for different lengths. It doesn't really mean anything. So we mark like the D2s and D3 using different colors. Yeah, that's all it is. All right. So I'm going to say a few things about the RP infinity methods. So notation, I like S0 denotes the sphere spectrum. P upper infinity, lower 1 by the suspension spectrum of RP infinity. We put the lower 1 here because stably the bottom cell is really in dimension 1. And also the P lower and upper n plus k to be the suspension spectrum of the quotient. So the bottom cell will be in dimension n and upper cell will be in dimension n plus k. So we denote the x of x to be the atom's E2 page of x. Oops. And T is the transfer map from the suspension spectrum of RP infinity to the sphere spectrum. So there's a theorem by Karen Pretty showing that this map is surjective in positive stems. And there's an algebraic analog of this. So this transfer map has atoms situation 1, so that's why you see this actual +1 in here. So it says that on the atom's E2 page, this map is also surjective on all positive stems. So both of the theorems were actually conjectures of Mark Mahavir's when he studied the metastable range of the unstable homotopy spheres. It's quite amazing how he came up with those conjectures by just computing some X group of RP infinity and so forth. Yeah.
What is the transfer map?
it's just the standard saying because RP infinity is like BZ2, so you can define it as that way. Yeah. So the idea is the following. So because this map is surjective, so if there's some differential we want to prove in the atom sphere sequence for sphere, that means the source and the target will all have like non-trivial pre-images. So if something happens in here, there must be something happens in here. And the question is, how do we compute like atoms differentials in RP infinity? Well, this is really generalizing Mahavir's trick for covariant eta earlier. So if you're a cell complex like RP infinity, one thing we can do is there's an atom spiral sequence like that. And then from the cellular filtration of RP infinity, we can form the algebraic Atiyah-Herzberg spiral sequence, where the E1 page is a copy of the X of sphere for different dimension. Or we could run the homotopy Atiyah-Herzberg spiral sequence, go over here, and use the cell-wise atom spiral sequence go like this. So if this P infinity is just the covariant eta, that is the chart I showed you earlier, so where the boundary homomorphism gives you the differentials in those two Atiyah-Herzberg type spiral sequence. So what's good about this thing is that all the differentials in the algebraic Atiyah-Herzberg spiral sequence can be computed by massive products. Or you can even use the lambda algebra to or make a computer program to compute it. And the differentials in this spiral sequence can be, in theory, computed by total brackets. Then if we know enough about the sphere, like Sternweisler, and we know those two information, then we can try to diffuse some information over here. So that's the idea of the Mahavar square. So now is our strategy of proving differential from sphere to RP infinity. So first we want to leave that differential we want to prove to RP infinity. Then we want to trace the differentials through certain subquotients of RP infinity using as few cells as possible. So the point here is that RP infinity, like we know all the primary attaching maps. Those are all in the image of J. So we can try to do something like that. And hopefully the final thing has like very few cells. And we want to establish that final differential in some finite state of a complex, and then we use naturality to push the one to prove the original one in sphere. So this method is, in the following sense, inductive. It's not a very strong sense, it's very weak, but it's kind of inductive. The point is here is the target and source elements in the final differential will have strictly lower stems than the ones in the sphere, because RP infinity start with the bottom cell start with 1. So any elements in here, if you go back here, the cell it comes from will give you a lower stem. So here is one example how this works. So this is one differential we proved from 61 to 60. So D3, B3 are elements in the E2 page. So there are a lot of like names for the spiral sequence. Like it's very standard up to 70, but it's not very systematic. We start to use like H like little letters, then we gotta use capital letters. Then when we run out of letters, we use sub-index. But anyways, those are well-defined names for some elements. So you see like 7 blocks. So each block is a differential in the spiral sequence of some spectrum, some subquotient of RP infinity or sphere. So we like push it back, go around, go some zigzag. In the end, we have the 2-cell complex, which is suspension 14 of covariant eta. And there's the differential. So the bracket 16 means it comes from the 16 cell, and 14 it means it comes from the 14 cell. So the point is that those two differentials are in the same stem. So D3 is in 61, and H4 cube is in 45. 45 plus 16 is 61. And this element is in 60, B1 is in 46, 46 plus 14 is 60. So we know that the differentials in covariant eta correspond to eta extension in homotopy spheres. So it turns out like we do have a non-trivial eta extension from H4 cube to B1 in sphere. So therefore, this differential is something we can establish. Then we use naturality, push it in here, and pull it back and push it forward. So that's basically the idea of our proof. Like, yeah. So it took us like 40 pages to prove this one differential. But it's worth it, because there are some geometric application in here. So together with 2 other differentials we proved, so Gordon Wang and myself, we proved that the 2 primary 61 is actually 0. So following Cavera and Milner, this means the 61 sphere has a unique smooth structure. Also, following recent Hill-Hopkins-Ramnell solution on the covariant element, this means this is the last odd-dimensional case. So only S1, S3, S5, and S61, those are the only odd-dimensional spheres that has a unique smooth structure. Okay, so now I'm going to move to the second method, the motivic covariant method. So motivically, the homology of a point is bigraded. It's proved by Wawolski. The mod P coefficient is Fp adding tau, where tau is this map between P completed motivic spheres and lives in the Hurwitz image of the motivic and Ellenberger-McLean spectrum. So I think some people call this the Tate twist. So now we can define C tau to be the covariant tau, which is a motivic two-cell complex. A starting point of all this method is a theorem by Dan Isaacson. He found out the motivic Adams-Novikov spiral sequence for covariant tau collapses for filtration reasons. This immediately implies that the homotopy groups, the bigraded motivic homotopy groups for covariant tau, is actually the X group over BP star BP. So that is the classical Novikov E2 page. So this is how the grading works. So note that classically in here, like if this number is odd, then the whole group is trivial. So only the even part sort of matters. So what's interesting is that, so one is an algebraic object, like in here. The other one looks like it's like homotopic. And for each gadget, there is a spiral sequence that converts to it. So as we mentioned earlier, like this I is the maximal invariant idea of BP star. So giving this filtration, we have the algebraic Novikov spiral sequence converting to it. And we also have the motivic Adams spiral sequence converting to the motivic homotopy of covariant tau. So the one collapses is the motivic Adams-Novikov, but the motivic Adams does not collapse. So both are very complicated trigraded spiral sequences. So Dan Isaacson, when he computes the stable stems up to the 59 stem, he also computes this covariant tau up to the 59 stem. So we have this data. So recently, Gordon Wang made a computer program that computes the algebraic Novikov spiral sequence. So this is purely algebraic. So what happens is into an even bigger range. So when you look at the data, they have the same data. So that was a really surprise. So this cannot be a coincidence. It must be something in general. So Bogdan Gregory, Gordon Wang, and myself, we proved that the two spiral sequences are actually isomorphic. So it turns out this theorem is actually very useful in the following sense. So the differentials in the algebraic Novikov spiral sequence, they're all algebraic. Like you can compute by the Gordon Wang's program, for example. But the motivic Adams differential for covariant tau is like a priori topological, like because those are Adams differentials. So therefore, we have a way to produce like topological differentials in quotes to from algebraic data. So recall that we have the Miller square in the classical case, and Miller proved that the algebraic Novikov D2 differentials correspond to the classical Adams D2 differentials. So now, in the following sense, we can generalize this theorem through the motivic setting. So what happens is we have the algebraic Novikov spiral sequence like in here. Our theorem tells us this is the same spiral sequence as the motivic Adams spiral sequence. So since covariant tau is a two-cell complex, we have a map of the inclusion of the bottom cell. So that gives us a map from the motivic Adams spiral sequence of the sphere to the covariant tau. Then we can take the real Betti-realization and go to the classical sphere. So therefore, if we start with any algebraic Novikov dr differential for any r, it doesn't have to be 2 now. Our theorem says that that's exactly the motivic Adams dr differential for covariant tau. Then we can pull it back using naturality, which gives us a presumably shorter differential, dr prime, in here. Then we take the Betti realization to get a classical dr prime differential in sphere. So through this naturality and zigzag, we have a way to produce classical Adams differential from the algebraic Novikov through the motivic board. So So the motivic homotopy theory is more about like using homotopy theories to do things in algebraic geometry, and we're kind of doing the other way around. So we also find a theoretical reason for this to be true. So let's take the cellular module spectral over curvature tau, whose motivic BP homology has bounded Chow degree. Chow degree means the topological dimension minus twice the weight. So let's also consider the p-completed BP star BP comodules, which are concentrated in even degrees. And this would be its bounded derived category. So as you might know, I graduated from University of Chicago. So by definition, I'm not a infinite category kind of guy. but here's what we got. So Bogdan, Gregory, Gondremont, and myself, we proved that those two categories as stable infinite categories with T structures, they are equivalent. And the restriction on the heart is by taking the motivic BP homology. So what we did is that we defined a T structure on the modules over curvature tau, and we identified the heart to be BP star BP comodules. So which is like great. But then we run into a problem. So trust me, as a Peter May student, I tried really, really hard to not use stable infinite categories. But my collaborator convinced me this is the way to go. So the problem with the triangular category is that when you have a T structure, you identify the heart, you don't really have a functor from the derived category of the heart back to the triangular category start with. But in this setting, you do. And what's even better is that there's a theorem in Jake Blue's book, Higher Algebra. There's a criterion in some homological condition. If that's true, it's also produce a equivalence. So we check that condition using the collapse of some motivic Adams Noether supersequence, just like the case for curvature tau itself. So that's how we got this theorem. And based on this theorem, in the homotopy category, we can just have the towers of the algebraic Novikov towers in here, and use this functor, we can get a motivic tower. It turns out to be the motivic Adams tower for curvature tau. So that's how we prove the equivalence on the spare sequences. So in the last 10, 15 minutes, I want to show you like how effective this method is. So now you're looking at the classical Adams spare sequence only up to the 45 stem. So now this should be considered as an easy range. So from here to here, like up to 13, there's really no differentials at all. Then you start to have this half invariant 1 differential, and the differential related to the image of J. And near the vanishing line here, there's a bunch of differentials which are closely related to the image of J, as you heard in Hinz-Miller's talk. And there are also some lower filtration differentials, so some of them are like very hard to compute. So I'm going to mark 6 of them as like harder differentials than the other ones. So maybe I have time, so I can write something on the board. So can you guys see in here? Right. So the first one is this one. So this is the half invariant 1 differential. And the one right above it, the D3, I have an arrow over there, is that. So what are other ones I marked? Right, that. Okay. So D3 of, what is that? R equals to H1 D0 square. Okay. And D3 H2 H5 is element H0P. D4 of H3 H5 is element H0 times X. We also have this D3 on E1, which is H1 times T. So I mark those two because those are the starting point of all differentials. So this can be proved following the half invariant one problem. I guess the easiest proof is that to realize this thing really detects like twice sigma square, which has to be 0 because sigma is in pi 7. So sigma times sigma must be minus sigma times sigma. So therefore, it's the only way to prove it. And you can prove the rest of them using Bruner's square zero method. So you can also just compare with Toda's unstable computation to realize this must be true to force this differential. This one, we also have several proofs. Like you can compare with the image of J. I'll know that this element kappa must have like twice it equals 0 by knowing the Toda's range. So this D0 is detected by kappa. So we have various proofs for each of them. So this one is related to the covariant invariant element theta 4 in pi 30. So this is differential preventing Peter May go to a bigger range. So at that time, he didn't know if this element survives. So those two differentials are also very interesting because they're all like the multiples of the h's. So this is kind of equivalent to the fact that this P detects like nu times theta 4. And this is kind of equivalent to x detects like sigma times theta 4. So those are both like non-trivial extensions on the covariant invariant elements in here. And this one was actually an error in Barrett, Mahover, Tangara, and later was proved by Bruner. So this is what I call a Bruner's differential. So he used this, he's deducing this from the D2 on E0 being H1 D0 and apply the square zero like power operation technique to get that differential. So those are the 6 differentials I have in here. So now I want to show you how the Coffey-Patel method can be used to prove those differentials. So this is the Motivic E2 page for Coffey-Patel. As you can see in the pointing arrow here, that gives us the half invariant one differential. So this one is check. Oops. All right. Now if we go to the E3 page, you see 2 other differentials. So if we zoom in, you see the one on, I guess I have really zoomed in to see the index, like H0, H4 to kill the H0, D0. And if you go later, you also see this differential, D3. If we go up here, oops, I'm sorry. You see this one. You see the Bruner differential instead of that one. So the E3 page of the Coffey-Patel checks 2 more differentials. Now if we go to the E4 page, you see another differential in here. So that gives us the D3, H3, H5 differential in here. So using all the Coffey-Patel spare sequence, we have proved like 4 out of 6. What's even better is that if we go to the infinity page, the non-trivial extensions in Coffey-Patel is exactly the product structure on the Novikov E2 page. So that's also something Gordon's data can tell us. And you see this extension on H2, H5. If you play this Mahover's trick on Coffey-Patel smash Coffey-Eta, the 4-cell complex, that will give you this differential in here. So using the Coffey-Patel method, we can compute up to the 45 stem, like 5 out of the 6. That leaves 1 behind. It's actually great news that leaves 1 behind because this does not violate the second Mahover uncertainty principle. Like otherwise, things will be too good to be true. I'll stop here. Thank you.
Any questions for Zhouli? So you're up to the 90th stem in the classical aspect
both classical and motivic, yes. So, yes, there are certain conditions on 93. If that's true, then that implies the existence of theta 6. We haven't been able to get that yet. Yep.
Theta 6 itself is in 126 still. I'm just saying that.
Yep.
But he has some way of reducing the problem in about 30 steps.
Yes? Sorry, say that again? I mean, like that condition only have some chance to produce theta 6. Yeah, so I don't know. Tyler.
Does this co-fiber tell does it tell you anything about the 40-page differential?
Sorry, I didn't hear the last part of the sentence.
Does the co-fiber method tell you about the differential between 60 and 61 from your other?
Yes, it actually does. So, like, I get questions like this, like, since those are very complicated, people make errors all the time. Like, how do you know you're not making any mistakes? Well, I don't really, but like, one thing to do is that, well, I got two things to say. One thing is that, so for any differential, we'd like to have as much proofs as we have. So that's kind of it feels better, right? So that differential we proved using RP infinity in 6.1, it also just comes out of co-fiber tau. So we have at least two proofs for that differential. Another thing is, like, in the computation, it sort of like self-corrects itself. Like, if you do something that doesn't look right, in 20 steps later, it will find a contradiction. So, but it does prove that 40 pages differential, so that's good. Yeah. Okay, good.
Are these connections with the motivic case something that could be useful at odd primes also, or is it just
So that statement of the stable infinity categories is at all primes. But I'm not sure how effective this method is at all primes because the Cartan-Ehrenberg already collapsed at all primes. Yeah.
Why would stem 93 tell you about theta 6? Is theta 6 can it be written like as a total bracket of or something like that?
Right. So there's little bit of history here. So theta 5 is in 62. So this is proved by Barrett, Jones, Mahoward. So interesting is that at that time, they only know range around like 45, 46, 47, like partial information later on. But they still managed to prove this existence of theta 5 over there. So if you think about this, is around like 3/4 of the range. So what happens is that they construct a cell diagram, something like this. So if you want to get theta 5, you can put something like here as a fourfold bracket suggested by the Massey products. But unfortunately, this obstruction, this primary threefold total bracket does not contain 0. It contains like eta theta 4. Then you have eta theta 4 is in something like that. Then they plug in 2 more cells to kill this obstruction. But then you realize there's 2 more obstructions you need to check. This one is in pi 16, this is in 30. So if this thing in pi 46 is 0, then things will be good for this primary obstruction. But they couldn't show this is 0. Instead, they show something like all elements in here can be written as something like that. So therefore, instead of having this, they put in 2 more cells. And then they check this threefold matrix total bracket as something in pi 47, and they still couldn't decide it, then they put in 2 more cells. So in the end, it's a 9-cell complex in the middle, and the composite is really give you pi 62, but the information is used in here. It's kind of a similar thing I want to do, because like if you divide, we don't know if this exists or not, but it's in 126. You do 3/4, it's around like 93, 94, 95. but we haven't been able to succeed over there.